Hi, and welcome to module number 40. In module number 39, we discussed the concept of sparsity, that there are bases for certain types of signals for which those signals representations are, for the most part, the coefficients are close to zero, small, and just a few coefficients are large, and that allows us to perform things like nonlinear approximation. And sparsity leads us to the question of what's a good basis? So we want some sort of energy compaction. We want the signal to be approximated well using a small number of large coefficients. So imagine that you're taking a transform, and you're then, after having computed the coefficients, you sort them. Orthonormal bases preserve the energy. That's known in undergraduate signal processing as the Parseval relationship. And we want the k largest coefficients to contain most of the signal energy. So to make this clear, the Parseval relationship is saying that the transform of x, the energy of the transform of x, is the energy in x itself. So, so let's see some examples of this. In the Fourier domain, energy of x is going to be sum over n going from 1 to n of x of n squared magnitude, and Fourier of x, which is often going to be denoted by capital X, is going to be, let's say, Fourier at frequency k will be something like sum over n going from 1 to n, x of n multiplied by exponent of minus j 2 pi k n over capital N, the length. And the energy of x of k, similar to before, is going to be sum over the k's are now, we have capital N k's, and we take the squared magnitude of x of k. And these are equal. The squared magnitude is equal. So what this implies is that if I have a signal x and I run it through a low-pass filter and I get, let's say, x prime, well, another way of thinking about that is that I ran x through a Fourier transform, giving me capital X, and then, so the low-pass filter on top would be convolution, CONV, and in the lower box, I have a low-pass filter, meaning that element by element, I just keep the lower frequencies and throw away the other ones. And if my filtered Fourier coefficients are going to be x prime, then I'm saying, first of all, that the energy in lowercase x prime, the signal, and the lowercase and capital X prime, same energy. And moreover, the energy in the part that was thrown away is also the same. So these ideas suggest that a good transform compacts the energy well, meaning that most of the energy is going to be provided in a small number of coefficients, and a bad transform spreads around the energy more evenly. And if it's spread around more evenly, we can't get the main highlights of the signal with a small number of coefficients. We don't have an informative understanding of the signal. And for a good transform, that compacts the energy well, a small number of coefficients will really give us a lot of insight, just like how in the machine learning material we were discussing how oftentimes we're willing to lose some precision in return for having a sparse model that provides us some understanding. So now, of course, it depends what type of data. For example, if you have a smooth 1D function, smooth signals, they have smooth derivatives. And in undergraduate signal processing, I'm sure that you discussed how these types of signals are well represented by the Fourier basis. Now, what if you have a 1D function that it's not smooth, it contains discontinuities. Now, the discontinuities, they contain a lot of high frequency coefficients, and because of that, the Fourier breaks down. It's no longer sparse, the Fourier representation. On the other hand, this motivates wavelets. Wavelets, as we're going to see in an upcoming module, are indeed well suited for 1D functions with discontinuities, and these types of functions are represented sparsely with wavelets. Now, what about that was 1D signals? What about 2D signal representation? So 2D signals, you can imagine images, and now there's more structure. There's structure not just in terms of discontinuities, but also around edges. The locations where there are discontinuities are structured locations. So one of the challenges here is geometry. We have discontinuities along 1D contours, and if we have separable 2D wavelets, separable meaning that we multiply a horizontal and a vertical wavelet, then the areas that are being covered are squares, and they don't capture the structure well. So here in our illustration, on the left-hand side, I have a signal that there's a discontinuity, and above the discontinuity it's white and below it's black, meaning a sharp discontinuity. And when we try to cover this discontinuity with squares, when we move from 13 to 26 to 52 squares, we get better resolution, better approximation, but we need quite a lot of squares. And on the other hand, the response of the signal processing community has been various types of type frames. Again, we're going to discuss frames, and what these frames actually do, they, instead of having squares that are separable, they have non-separable types of things that are not just rectangles, but rotated rectangles. And as we move to finer detail, the number one, the rectangles are thinner, because we already know from the coarser levels of approximation approximately where the discontinuity is. And number two, there are more angles. So because there are more angles and they're thinner, we can now specify at the higher degrees of resolution, we can specify the structure of the discontinuity very well. So let's pause for a moment and revisit our good old friend, in quotation marks, the Fourier basis. So here we have a picture of the celebrated French scientist, and recall from undergraduate signal processing, I'm sure that you discussed Fourier transforms both for continuous and discrete time. And they're transforms for periodic signals and also for aperiodic signals. And one of the highlights, one of the main reasons why Fourier analysis has become so popular in recent decades is that in the 60s, Cooley and Tukey basically reinvented a result that Gauss had already noticed around 200 years earlier, that the discrete Fourier transform can be calculated in theta of n log n computation. So having a fast transform which replaced a theta of n squared brute force approach is great for sparse representation of smooth functions. And as you can imagine, there are versions of the Fourier transform for multidimensional signals. As I mentioned earlier, there are separable transforms. But once again, there are other types of transforms too. And this gives rise to the question, why do these transforms work well? The main idea is an orthonormal transform. Orthonormal transforms have the great property that if we have a signal and we look at its coefficients with respect to this orthonormal transform, there's going to be a one-to-one mapping from the signal, perhaps in the time or spatial domain, to the transform coefficients and back. And all of this one-to-one mapping may sound obvious. Most of the things that I'm sure you've seen in signal processing involve one-to-one mappings. Sometimes there are types of representations that don't have that property, and we're going to be discussing some of them soon. So let's begin by understanding the basics, the orthonormal transforms. So we have a vector space, capital V, and it's going to have dimension n. And this is going to be an inner product space, meaning that the capital N basis vectors, V1 through Vn, if we take any two of them, Vi and Vj, and we calculate their inner product, if I and j are equal, the inner product is 1, else the inner product is 0. That's what an orthonormal transform means. 0 or 1. 1, the energy in each of the vectors individually, and 0 meaning the two different vectors are orthogonal, perpendicular. So why do we have this one-to-one mapping? So we can now express any vector x in our space, in our vector space capital V, which again, it's actually an inner product space with coordinates. So alpha I is going to be the inner product between x and the vector Vi, and there's a one-to-one mapping between V and alpha. If you have the V vector, you can get the alpha vector. If you have the alpha vector, you can get the V vector. Why is that? So let's suppose that x can be represented as a sum of alpha I Vi. So can be represented, okay? This doesn't mean that it's unique. That's the important part. Let's verify the formula for computing the coefficients. The inner product between x and Vi, recall that we want this to be alpha I, is equal to an inner product between, we substitute for x a summation over j going from 1 to n alpha j Vj. I just like to highlight that we're using j instead of the i's that we used earlier, because here we're using the I for the vector Vi. And the inner product has the property that an inner product is linear, meaning that an inner product over sum over alpha I Vi's and anything, W, is equal to a summation over the i's, alpha I, times the inner product between Vi and W. So this is correct for all W. All W in our vector space, capital V, which again is an inner product space. So we can now write that we have a summation of j going from 1 to capital N, alpha j times the inner product between Vj and Vi. Now recall that the inner product between Vj and Vi is either 1 or 0, 1 when I equals j, 0 else, and therefore when j is equal to I, alpha I is multiplied by 1, and for the rest of the time when j is different from I, we're multiplying something by 0, and something finite times 0 is, although we have n minus 1 of them, they're all going to be 0. So overall, this entire summation gives us alpha I, and we can see that we can go from x to alpha I and back. So here's an example. So we understand that orthonormal transformations are useful because we have a one-to-one mapping. We also understand that they preserve energy, the Parseval. That's good. So they're useful, but let's see some examples. And one example is the discrete Fourier basis. We have an input signal x of length n. It could be real valued, or just to make this more interesting, it could also be complex valued. the Fourier basis vectors, basis vector k, vk, at time n is 1 over square root of capital N. So I may have missed this normalization term earlier. Exponent of minus I or j, that's the square root of -1. 2 pi kn over capital N. So the k and the n are indices of our vector. Now the time index n within the vector is within the vector vk, and k is the index within the basis capital V. Now, similar to before, I was discussing the energy. The norm is defined as the squared L2 norm of vk is a sum over the n squared magnitudes of vkn. And if you think about it, if you have exponent of I times something, its magnitude is equal to 1, and its phase is equal to that something. In other words, polar coordinates. And if the magnitude of that thing is 1, then the magnitude of that thing multiplied by 1 over square root of n gives us 1 over square root of n. And recall that we're squaring the magnitude. So we have n components. Each of them is 1 over square root of n squared. So n times 1 over n is 1. So what we just demonstrated is that for all the vk's, so k can be elements of 0, 1, 2, up to n minus 1. For all of these different values of k's, the norm of vk is 1. Now we also want to show, so it's in the orthonormal word, they're normal, they're normalized. But we also want the ortho part of orthonormal, that we want to show that the Fourier vectors are orthogonal. So let's take vk and vj, where k is different from j. Let's calculate the inner product between them. That inner product is a summation over vkn multiplied by the conjugate of vjn. Now, I'd like to highlight that for complex valued vectors, the inner product space involves taking the conjugate of vj. And if this was a real valued inner product space, we wouldn't need to take the conjugate. The conjugate of a real valued number is itself. So overall, let's understand what we have here. vkn times vjn, let's type this. vkn times vjn is equal to 1 over square root of n times the exponent of minus I 2 pi k n over capital N multiplied by the same expression, but we're going to use j instead of k. This is equal to the 1 over square root of n's. We have two of them, become 1 over capital N. And exponents are multiplied minus I times 2 pi. Or rather, this should be conjugated. And the conjugate gives me negative j instead of j. We take the negative of the phase. Now, minus I times 2 pi negative j n over capital N is plus I 2 pi j n over capital N. So overall I have exponent of I 2 pi n divided by capital N, and we're having from the first expression we have minus k, and from the second expression we have plus j. So now we have a summation 1 over n, summation over capital N terms, exponent of something that depends on k times exponent of something that depends on j. And what we expressed earlier was exponent of I 2 pi n over capital N, all of this to the power of j minus k. Now, this expression is actually a root of unity, a root of 1 to the power of n. And if we visualize these, the horizontal axis is going to be the real part of the complex plane, and the imaginary part of the complex plane is going to be illustrated along the vertical axis. And we're going to have the unit circle, 1, -1, -1, 1. And the 1 location, I'll just change color, will be located here. And there are 2 pi radians of phase, 360 degrees. And the first root is going to be at phase 2 pi divided by capital N. And this is going to be the nth root of unity. And when we take that to the power of j minus k, and recall, we're summing them up, so we're summing over that value and that value and that value, and they're spread uniformly around the unit circle. So they're centered around the origin. And because they're centered around the origin, the sum is 0. So you might ask, well, why are these one-to-one mappings helpful? One useful result is that all linear transforms T over an inner product vector space capital V can be represented by a matrix, because we have this orthonormal one-to-one mapping. We can express X, the relation from X at the input to Y at the output, as a multiplication by a transform. And matrices are, they're convenient, right? A second result is the spectral theorem. The matrix representation yields eigenvectors. Eigenvectors have the property that when we pass them through the system, they're merely amplified. They may be amplified by a number that's greater than 1 in magnitude or less than 1, so attenuation or magnification. There may be a phase shift, but overall, all that happens to these eigenvalues is that they're amplified. That's it. So at the input, we have a summation over alpha n vn as before. And now this is a spectral theorem is telling us that this is a linear operator, and each of the vn's is going to be an eigenvector, and each of the eigenvectors is going to be multiplied by lambda n. So instead of alpha n at the input, we have alpha n times lambda n at the output. Every coefficient is amplified. That's it. And it turns out that linear time invariant systems are helpful along these lines. So first of all, they're common in applications, as we've discussed in the class multiple times. Many systems, many real-world systems are approximately linear. It could be that we're linearizing around a working point. That's the style in many analog circuit types of analyses. Or it could be that we have a man-made system that over decades has been kind of optimized to have a near linear response, for example, linear amplifiers. So these things are common in applications. And of course, many real-world systems are time invariant, meaning that if you shift the entire experiment by a year, the output will be shifted by a year. And for linear time invariant systems, we have exponential eigenvectors. So the eigenvectors are basically sinusoidal. And the spectral theorem tells us that sinusoids are eigenvectors of linear time invariant systems. As a byproduct of all of that, smooth signals, we understand that they have sparse Fourier representations. And because of that, we can filter them using LTI systems. We can keep the smaller coefficients, the lower frequencies, and we can assume that the higher frequencies are primarily noise and attenuate them. But of course, many signals are not smooth, and signals that have discontinuities, they contain a lot of bandwidth, and that's where we're going to look in subsequent modules. So that'll be it for module number 40.